So far, we talked about the most important concept if you want to design an autopilot for a flying aircraft. The first is development of linear design models. How do you come up with a linear models that are fairly accurate and that will work for most of the times? And the second topic, which I sort of discussed in last class, was related on how to design the autopilot. And in the last class, I showed you the slides, showed you the material from the textbook, and threw bunch of equations at you. But I did not spend enough time on explaining what that each and every equation means, or if I ask you to implement that code onto a microcontroller such as Arduino, what exactly would you do? And how would you use the same microcontroller and then have that microcontroller fly different types of fixed wing aircraft? Believe it or not, this is something what we did in 2007, 2006, 2008 time frame when we implemented the autopilot on an Arduino. So what I want to do is I want to kind of give you the physics behind the equations that we talked in the last class. And then I would like to show you if you were to build your own autopilot, if you were to build your own flight stack, how would you do it? So in today's class, what I'm going to do is I'm going to go back and I'm going to dissect each and every equation to the point that you completely understand what that equation physically means. What is its implication in the terms of the aircraft control surfaces? When we say something needs to be controlled and you say that this transfer function, you're placing the poles, what does that mean in terms of implementing on an actual controller surfaces? Let me promise you this. If you understand the chapter 5 linear design models, and if you understand the autopilot, at least the successive loop closure, which is a very standard technique, you would be pretty good flight engineer in terms of robotics flight engineer. You would be able to design the flight controllers for different air vehicles. And again, this topic, so two topics that are super important is linear control models and basically the topic on the flight control system or autopilot design. If you are interested in applying to any aviation companies like Paulo Air, or if you want to apply to Honeywell Avionics, if you want to go to the Rockwell Avionics and Cedar Rapids, if you want to work at Boeing, Airbus, if you want to work there are so many EV aircraft startups that are coming, like they want aircraft to be flying on EV, electric vehicles, not just gas engines. So these two chapters, they give you the basic understanding of how to design the flight control. So please pay attention. Some of these concepts will take some time to digest or to grok. But if you pay attention, I promise you that that will be a good investment of your time. So now what I'm going to do is I'm going to give you a line by line explanation on autopilot design. Now, what do we want autopilot to do? First and foremost, I have a UAV, and UAV has north position, east position, and down position. And the UAV has, so these are the positions. And UAV has altitude. Attitude. Attitude is roll, pitch, and yaw. So roll. So basically roll, pitch, and yaw. So this is attitude, which is the aircraft angles. I want my autopilot to control the position and attitude. So that is the first and foremost fundamental function of autopilot. Whatever secondary algorithms or secondary control logic that you have, whether it's for path planning or whether it's for obstacle avoidance, whether it's for maneuvering, whether it's for morphing, that sits on top of it. So at the base of the autopilot, the core autopilot functionality is it should be able to control the north position, east position, down position, and roll, pitch, and yaw of the aircraft. However, very rarely the aircraft would fly when there is no wind. So what happens is usually there is some wind disturbance. There is some wind. And when you add wind, what happens is, even though the aircraft is heading in certain direction, let me grab my aircraft model. Even though the aircraft is heading in certain direction, because of the wind, its apparent direction gets changed. Its apparent direction gets changed. Even though the aircraft is trying to go like this, because since wind is coming in a direction like this, aircraft goes a little bit offset. So what happens is, when we are developing the control, the attitude is usually phi, theta, and chi. So this is the roll, this is the pitch, and this is the course. Now, if you have a manned aircraft, for an example, or if you have a simple RC aircraft, then what you can do is you can have a simple single axis wing leveling system. Single axis wing leveling system. What does that mean? Is basically if it pitches, if rolls, then basically that stabilization system can stabilize it to its previous position. And this is a very simple flight stack, a very simple IMU based flight stack that would change the control surface inputs, basically the servo inputs, basically PWMs to the servos that would adjust the wing levels. Now, there are quite a few flight phases that we need to think about. And the flight phases typically and we are not talking about the fighter planes or dogfights. We are talking about commercial planes or a simple transportation planes. You have something called as takeoff. You have ascent. You have level flight. You have descent. You have approach. And you have landing. The first and foremost assumption when you are trying to design a control system for an aircraft is first assumption, and please understand, this is an assumption, is we assume that the longitudinal dynamics of the aircraft and the lateral dynamics of the aircraft, they are separated. So which is basically we can independently control the longitudinal dynamics and we can control the lateral dynamics, longitudinal and lateral. Now, I need to specify, because I'm going to explain, we are going to open the flight control loop and we are going to look at each and individual term. So for my own reference, let me specify what happens when the aircraft is flying. So let's consider that this is an aircraft. Okay, this is an aircraft. And this is an inertial axis. So this is going to be my I. This is my inertial axis. Now, if you look at the body axis, this is going to be my IB, which is my body axis. Now, if you think about the way the airspeed is, so if the aircraft is going forward, the airspeed will not be aligned with the body axis. So airspeed would be something like this. So I'm going to show you, this is the airspeed, which is VA. VA stands for the velocity of air with respect to, or aircraft velocity with respect to surrounding air. And it doesn't matter whether you look at aircraft stationary and wind flowing, or if you consider wind stationary and aircraft flying. So it doesn't matter from dynamics point of view. Then typically you have something called as wind forces. So you have wind. And VA plus VW gives you something called as the VG, which is the ground speed. So VA is the airspeed, VW is the wind speed, and VG, which is VA plus VW, is the ground speed. Now, a simple definition of ground speed would be speed of aircraft as if aircraft is on ground. Now, what I want to do here is I want to specify few angles, and these angles are very important for lateral dynamics. So first and foremost, let's understand the heading. So this is the heading. This is the heading. So heading means the angle made by the body I axis with the inertial I axis. So this is the value of heading. Now, if you look at the angle made by the body I axis with the airspeed, this is called as the beta, which is the side slip angle. This is, so beta, so psi is heading, or also called as yaw. Beta is side slip. Now, please understand, wind is missing the direction in which aircraft should ideally be going. So what you do is, if you look at this complete angle all the way from here to here, this is called as chi or course. And the crab angle is the difference between the chi and the course. So crab angle, so this guy, chi C, is called as crab angle. Now, when the aircraft is flying, when we look at the aircraft flight dynamics, we need to control the lateral motion of the aircraft, and we need to control the roll motion of the aircraft. So basically, I need to control the course angle chi, and then I need to control the lateral dynamics of the aircraft. So what we are going to do is, we are going to assume that even though in theory, aircraft longitudinal dynamics and aircraft lateral dynamics is coupled, for controller, we will assume that those are independent. So aircraft longitudinal dynamics and aircraft lateral dynamics can be decoupled and independently controlled. Clearly, this assumption is not valid for fighter aircraft, or it's not valid for aircraft performing complex maneuvers. But if you look at the flight phases that we talked about, this assumption can be valid. So next assumption, what I'm going to say is the longitudinal dynamics and when I say longitudinal dynamics, the important variables are forward speed, pitching motion. Pitching motion stands for pitch roll, the pitch angle and pitch rate, pitching motion, and climbing. And why is this important? Because when you look at the transfer function would include the terms that is related to forward speed, pitching motion, and change in the altitude. Now, so lateral dynamics is rolling and yawing. So what I'm going to do is I'm going to somehow independently control this dynamics and independently control this dynamics. And in the rare event that in some flight regimes the aircraft is transitioning, then I would design some type of a coupling. Now, in the last class, believe it or not, at least 10-15 times, I talked about the concept of a successive loop closure. If somebody wants to make my day, or for that matter night, can someone tell me what is this successive loop closure? Okay, how do you exactly do that?
Loops input and output being coupled. Not one system's input will be other system's output.
Yeah. Okay. So clearly I didn't do a good job last time.
And then you have to model the inner ones that's always a one-to-one. Like
okay.
Each inner loop is
yeah.
Focusing on stability first.
Okay. So let's converge, which means your answers are right, but let me give you what that means. And this is exactly what happens when we teach calculus by showing PowerPoints. Equations should not be taught by showing PowerPoints. Equations should have physical meanings and interpretations. Otherwise, if somebody wants to know what happens otherwise, I recommend watch a movie, 3 Idiots. That is available on Netflix with subtitles. So now, right now, what I'm showing you, this is my uncontrolled system. And uncontrolled system has these transfer functions, P1S, P2S, and P3S. Clearly, this is an open loop system. And our last entire chapter was devoted on how do we come up with simple models that describe P1, P2, and P3. And these could be like control of aileron, then outside using ailerons to control the heading, using heading to control something else. So basically you have this cascaded transfer functions. So what this means is you have this dynamical system, you have this second dynamical system, and you have this third dynamical system. Everyone understood this? Last chapter, chapter 4, was entirely devoted to how do we convert that, how do I take those 12 equations and finally represent them into a dynamical system that is represented as single spring mass damper system that is acting on an external force. The equation form would resemble to what we have as spring mass damper system. And in certain cases, basically, in certain cases, the output would be displacement. In certain cases, output would be velocity. In certain cases, the output would be acceleration. And this point is important. I need to explain you this. So first and foremost is I have these three dynamical systems that are part of this overall aircraft. This is the aircraft. So, but these aircraft have these subsystems. These subsystems are cascaded, but I simplified those subsystems to the point that at the end, I have a spring mass damper system. So my first dynamical system is a spring mass damper system. My second dynamical system is a spring mass damper system. And my third dynamical system is also a spring mass damper system. Are you with me so far? Now, in terms of control, what I want to do is, if you have an aircraft or if you have an object, what you have is you have certain input and you have certain output. So this is an output could be x of t. Output could be x dot of t. Output could be x double dot of t. X double dot of t. So what I'm trying to say is, even though you have the spring mass damper system, it will have the structure, and please understand the nature of input could be different. It could be a random input, sort of a disturbance. It could be a step input. It could be a constant input. So when I say u as a function of t, imagine that it could be a sinusoidal input, it could be a random input, it could be a ramp input, it could be something else. But important point that I want to tell you here is, the difference is, even though these systems are represented as spring mass damper system, the output that we are measuring could be the displacement, could be the velocity, or could be the acceleration. What that means is, imagine if I have a displacement sensor on this first system, that will give me the value of x. If I have a Doppler radar on second system, it will not give me displacement, but it will give me velocity. And on the last system, I stick an accelerometer. I will not get displacement, I will not get velocity, but I would get acceleration. Everyone understood this? What does that translate to? It translates to the denominator of the transfer function would remain same, but the numerator of transfer function would be different. What that means is, can someone tell me the very definition of transfer function? Transfer function is nothing but Laplace transform of output divided by Laplace transform of input. So what I want to tell you is, I want to show you a couple of things here. And the reason I want to make this absolutely clear is, if you decide, hey, I want to build a plane, a paper airplane, okay, and then I want it to fly autonomously, you potentially can. You will have to do a little bit of wind tunnel experiments, but you can. That is how the Wright brothers flew their Kitty Hawk. So let me tell you what this means. So imagine that you have this spring mass damper system. K, C, and M. And there is some input U of T. And I'm going to say that first I'm measuring X of T. Okay, my output is X of T. So if I write the differential equation, it is going to be mx double dot plus cx dot plus kx is equal to u of t. Any questions here? Everyone okay? Now, what I'm going to do is this equation, I need to convert into transfer function form, or I need to take the Laplace transform. As soon when I take Laplace transform, it becomes ms square x of s plus c s x of s plus k x of s is equal to u of s. Are you with me so far? My output is x of s. My input is u of s. So I can write down equation something like this. X of s divided by u of s is equal to maybe 1 divided by m s square plus cs plus k. Are you with me? Where m is a constant, c is a constant, k is a constant. Sometimes you will see this equation written in something called as the canonical form. Canonical means representative. Canonical means representative. The canonical form would be something like 1 s square plus 2 zeta omega n s plus omega n square s, omega n square. And canonical form means this is the standard form where a second order transfer function is represented. That is how that is discussed. So again, quick recap. My output is the displacement. Now, what would happen? What would happen if my output is velocity instead of displacement? What if my output is velocity? Do you agree with me? I have this so I have this equation. Xs is equal to this guy, and please understand this because this is very important. Omega n s plus omega n square multiplied by u of s. So in x of t becomes x of s. Do you agree with me? X dot of t becomes s x of s, right? Which means instead of displacement, if I want velocity, what I would do is I would multiply my left and right hand side by s, and all of a sudden now I have a transfer function which is velocity of s divided by u of s. The only difference is this is like s square plus 2 zeta omega n s plus omega n square. Everyone understood this? If I were to do that for the acceleration, what would have changed? This will become a of s, and instead of this s becomes s square. Everyone understood this? Now, imagine you have a sensor, okay? But that sensor is not giving you the absolute value of the displacement. For an example, displacement will be 1 millimeter. Displacement will be 10 millimeter. But that sensor is giving you an output in terms of voltage. So do you agree with me? It is possible that that sensor may not give me the output in the units of displacement. It will give me output in something else. So the change then will be that instead of 1 here, there will be some constant k. And this is just a gain. And this gain indicates that how the measured quantity, how the actually measured quantity is related to the measure rand, the quantity which I want to measure. So what I get and what I want is related by this gain K. Everyone understood this? And this K can be of different form. So basically, if this K and this K is the same, do you agree with me? I can write this equation, and I want you to remember this. I can write this equation something like omega n square divided by denominator. Do you agree with me? So if somehow I tune the gain, or the gain of my system is related to omega n square, or is equal to the stiffness matrix, then I would have omega n square in the numerator, and I will have some values in the denominator. Important point. The first transfer function will become 0 for certain values of f. I'm sorry, first transfer function will become 1 divided by 0 for certain values of s. Do you agree with me? Do you agree with me or not? So and those are called the poles of the transfer function. So that value will become 0, and that is the pole of the transfer function. So if transfer function becomes infinity, 1 by 0, that is the pole. But no matter what I do, the numerator of the first transfer function will not be 0. So which means the first transfer function has some poles but no 0. The second transfer function is s square, which means there is one value of s. S is equal to 0. So it actually has 1 0. And if you have equations like s square, s cube, that tells you the number of zeros that you have. And this is an important definition. So for s, when denominator is 0, they are poles. And for s, when numerator is equal to 0, they are called zeros. Are you with me? With this background, we are ready to handle successive loop closure. Now what I want to do is, I want to add a control system, somehow some type of a control system. And I'm going to show you today an alternate form of PID control, okay, which is super useful and very, very practical. So what I want to do now is, since I have P1, P2, and P3, I'm going to start something like this. First, I'm going to consider P1. So I have P1 of S. P1 has some input U1, has some output Y1. I'm going to add a compensator or a controller. I'm going to add a compensator or a controller, C1S, and then I'm going to add the summing junction over here. Please understand, it needs to be a closed loop system, which means there has to be a feedback. The feedback is unity, which means the feedback gain is 1. It's a negative feedback. So this is negative, this is positive. So this is my P1. Now the next transfer function that I have is P2. So this is next transfer function is going to be P2 of S. And the control effort that I need to control P2 will be here, C2. Then repeat the same story. Add the summing junction, grab the feedback loop, and then do it. So what has happened? U1, Y1, then Y1 becomes U2. U2 is fed into P2, and you get Y2 out, and this Y2 gets fed to the summing junction, which is minus and plus, And if you want to control the next transfer function, then what you do the exact same thing. You add your P3 here, and then you add your controller block. Now, what I'm going to do is the important part here, which I want to show you, is I have designed this compensator, or I have designed this controller so that the output of the first dynamical system equals the control of the second dynamical system. So basically, I'm going to design in such a way that this whole thing becomes one. So in other words, I would try to control the innermost loop. So that this is what it means in terms of successive loop closure. So first I'm going to design C1, and you will hear the terms interchangeably. They will call it a controller or they will call it a compensator. Typically, controller, in the case of linear control, they are like proportional integrative derivative, PID control. When you think about compensator, there is something called as the lead compensator and there is something called as the lag compensator. At the end of the day, both of those want to do the same thing. They want to control the response of the system. But PID controller, basically, they have slightly different structure than a lead and lag compensator. Again, at the end of the day, whether you use, again, a controller or whether you use a compensator, they finally do the same thing. So you will see these terms change interchangeably. So in some books, they will say compensator. In some books, they will say controller. Now, let's understand the practical limitations when we are implementing something like this on an aircraft control surface. So this is the controller or the compensator. Controller or compensator. Now what I want to do is, I want to actually show you what's happening in an actual aircraft. So I have this aircraft, toy aircraft, and this is the wing. This is another wing. It's a swept wing aircraft. And then what I have is I have these ailerons. Ailerons are like these flaps. And what happens is, if you look at the ailerons, these ailerons are attached to a hydraulic connector. So basically, you have this something as a manipulator, a linkage, or it could be just a cylinder. And what's going to happen is, as this cylinder goes forward or backward, this aileron is going to flap. So if you think about it like this, probably if you have flown in an aircraft, you have probably seen something like this. So aileron, they have a piston cylinder, usually hydraulic, and basically those hydraulic actuators, they change the orientation of the aileron. The practical application here is, the hydraulic actuator has a finite length. Hydraulic actuator cannot extend infinitely, which means hydraulic actuator is going to saturate at some control input. Now, what does that saturation mean? So typically, you are going to use some type of a motor control or some type of a control logic to excite that hydraulic actuator. And it may so happen that even though you are increasing the input, the actuator will not move beyond certain location. Think about it like you floor your gas pedal. So basically you floor it. You want the vehicle to go even faster, but the gas pedal is physically floored. It cannot turn anymore. So that would happen with the actuator. So what happens is, we have to be very careful about the saturation. So, and that saturation is typically implemented in something like this. So you have some control input, but if the input decreases beyond certain point, or if the controller is increased beyond certain point, the saturation, basically the control input saturates. Everyone understood this? Okay. Does everyone know about PID control? Okay, no review required. Okay, very good. Then what I'm gonna do is I'm gonna draw this transfer function. I'm gonna draw this transfer function. So this transfer function, now you have to tell me what does this physically represent? And this is very important. What does this transfer function physically represent? It's a spring mass damper system. And what is the output? Scaled displacement. Everyone understood this? This transfer function has a constant B naught, A naught, and A1. They are all constant. One constant in the numerator, two constants in the denominator. So this transfer function has no zeros and two poles. Now what I'm going to do is, this is the output, this is the input. And I'm going to add a control, something like this. And I want you to tell me whether it's a P control, whether it's an I control, or whether it's a D control. Believe it or not, this is the exact same flight architecture that was used for tilt rotor. So, okay, since you all know what is PID control and you have seen the MATLAB webinars and done project, I want you to tell me what type of control is this? Is this P control, I control, D control, PD control? PD control? Okay. Now, first and foremost, I mean, just don't answer the question because I use the KDs and KPs, okay? So, please understand this is not your conventional PID control. Because what happens in conventional PID control? In conventional PID control, you have a proportional gain, integrative gain, and derivative gain. They are all situated in the error term. So what that means is you have a term which is Kp times error plus Kd times error dot plus you have integration Ki dt. So integration Ki integration E dt. Everyone understood this? So which means your Kp, Kd, and Ki, all of them are acting on the error function. Error means actual minus desired. Do you agree with me? However, if you look at this particular operation, if you look at the way this controller is implemented, what you have is, let's look at what is happening as we expand this transfer function. So this is Y, you have YC. So what is going in here? Here you have YC minus Y. Do you agree with me? YC minus Y is the error that's get fed to Kp. That's get added at the summing junction and that's get fed as part of U. Now what is happening here? Y is coming here, but this Y is differentiated because this Y gets multiplied with S. So what you have is, here you have a derivative term, but it is not dependent on the error term, but it is dependent on the derivative of output. Everyone understood this? So what you have is Y is coming here, Y is going here. When Y gets multiplied with S, what do you get? you get y dot, right? And that basically y dot is multiplied with KD. So what you have is the control effort that you are getting here is not dependent on the error, which is yc minus y, but it is dependent on the output y. What? No, y is not error. Y is the, so okay. So yc is the basically you have some set point, and y is something actual, and what you have is this difference between these two is the error. Everyone understood this? Now, these are the type of controls. This architecture is actually preferred when you are trying to control the lateral dynamics and longitudinal dynamics rather than the classic PID control. Now, if you were to expand this, and I can do this, or I can just give you the expression, but let me show this to you. Just for the first case, yc minus y multiplied by kp minus kd times s times y multiplied by b naught divided by s square plus a1s plus a naught is equal to y. This is the total equation. And what we want to do is, at the end, we have to perform this mathematical jugglery and need to get y divided by yc. This is the control and the actual. So this is the transfer function that is basically relating to output and input. And error is the difference between output and input, by the way. So this becomes BO KP divided by S square plus A1 BO A1 plus BO KD S plus A naught plus BO KP. So when you solve this transfer function, and when you write the transfer function as output divided by input, you are going to get a transfer function wherein you have the controller term KD and you have the controller term KP appearing in this equation. Now, please try to understand, if you have anything multiplying S, that is relating to the damping. So if you increase the value of KD, then the damping will change. If you increase the value of KP, then the natural frequency is like you are changing the spring. So if you think about it, KP is like changing the spring and KD is like changing the damper. Everyone understood this? And some of you may ask me, what is the difference between this transfer function and the transfer function that is typically developed or generated through the PID control? And the answer to that question is, it's not. The only thing is, these terms, this BOKP, these coupling terms will be different. So if you were to derive this equation using like KP plus KD type of transfer function, you will get an equation that is in the same form, but from the implementation point of view on an aircraft dynamics, you will notice that the controller loop is implemented something like this. But this has a very important practical significance, and let me tell you what this practical significance is. So if I want to write down the controller effort, please note, this is my controller effort. This is my controller. And the control is nothing but, I have error KP multiplied by error that is coming from here, Kp multiplied by error that is coming from here, plus, minus Kd times y dot. What that means is if error is 0, then the majority of the control effort is governed by the velocity of the output, is response to the output velocity. And if y dot is equal to 0 or very small, then your control effort is controlled by the difference or error. Now, this gives me an interesting analysis or logic, which I want to talk about, is what exactly going to happen when you have a control input. So when you have a control input, say Umax, this Umax is going to be Kp times the error max. Now, what does that mean? Imagine you have a system and all of a sudden you provide a step input. So you have a system and all of a sudden you provide the step input. And what is this control gonna do is, control is going to sort of control this system response, something like this. It is noted that the error is maximum, which is this Emax. Emax is maximum at the beginning of the step input. And now, if I want to determine what should be the value of my Kp, if I want to determine what is the value of my Kp, what I would do is, I would find out the maximum error possible in all the flight regimes. I will find out the maximum error possible in all the flight regimes. And I will find out what is the saturation limit for the actuator. So what is the Umax? What is the maximum control effort that actuator can exert? And that control effort could be the extension of the actuator or the force that is provided by the actuator to achieve that deflection, or maybe the torque provided by the actuator. And that would allow me to find the value of Kp. That would allow me to find the value of Kp for that particular air vehicle. So this Kp would be specific to the vehicle. So you can find out the value of Kp based on the maximum error and maximum input, control input. At the end, please understand this equation is in the form of the second order control system, omega n square to zeta omega n. So what that means is, if you want to find out the value of omega n square, which omega n is going to be the square root of a naught plus p naught Kp, and then you can find out the value, and this guy, if you want to find out the poles, they are going to be minus zeta omega n plus minus I omega n square root of 1 minus zeta square. Now what that means is, if you want to control how far the system oscillates or how fast the system approaches, you can tune the value of Kd, Kp, and essentially tune the spring and tune the damping that is representing the aircraft dynamics. Yeah.
So the error maximum is user defined, like The internal loop, it would be the maximum angular acceleration that MATLAB can tolerate. The outer one would be the velocity, maximum velocity.
So that error is user defined. So again, depends upon what you are measuring and what you are supplying. So for an example, I will answer that question in the context of basically when we unfold the lateral dynamics, lateral control, then I would be able to answer this question in a better fashion. But at the end, what I want to tell you here is this approach would allow you to find out what should be your KP, what should be your gain that is given by the input that you can give and maximum error that is possible in this flight regime. That is what it means. But I'll answer your question more specifically when I actually unfold the lateral dynamics. Okay, so what we are going to do, the thing that I showed over here, we are going to do for each successive loop in the lateral dynamics, and we are going to repeat the exact same process for each successive loop in the longitudinal dynamics. The next question is, how would you implement this on a microcontroller? Microcontrollers do not work in a continuous domain, so time is discrete. So what you would do is, basically, you have this continuous transfer function that you will have to use something called as the Z transform and convert that into a discrete transfer function. And if you use the MATLAB toolbox, it can take a continuous transfer function, which is defined over here. This is the transfer function that is represented in a continuous form. This is not a discrete form. You have to use Z transform to convert this transfer function into a discrete form. And on the microcontroller, you will implement that equation in a for loop. And at every for loop, what will happen is you will get certain value of that control input, and that control input will get fed to an amplifier, and that amplifier would exert the amplified effort onto the control circuit. So that is how it will be implemented. Everyone understood this? Any questions, concerns, doubts? So this is the crux, successive loop closure. Now what I'm going to do is, I'm going to look at the lateral autopilot design. And bear with me because it's a little bit convoluted. But I'll go step by step. So first and foremost, at the end of chapter 4, we came up with this equation, big long equation for lateral dynamics. We linearized that long expression for lateral dynamics. And finally, we came up with a transfer function that was open loop transfer function omega. Omega n is the natural frequency for spring mass damper system. So omega n is if you have a spring mass system, then if you give it a perturbation, this is the frequency at which, so omega n is given as k by m. So physics 321. Okay, so, and I'm going to draw this. So first and foremost, we have this innermost transfer function a phi2, and these are all constants, s plus a phi1. Now what you have is, you have the aileron input, and this aileron input is controlling the angular velocity about x. P is the angular velocity about the x-axis of the aircraft. I'm going to add the summing junction, and then I'm going to pull this guy from here. I'm going to pull this guy from here and add a KD term, KD phi term on this. So KD phi term is a constant. So KD P term, and then I'm gonna add this term over here. So what I have is minus, and I have delta A, I have P. So if you don't know what P is basically the roll rate. When I integrate the roll rate, 1 divided by S, I get the roll angle phi. This is the roll angle. And then when I take this roll angle and multiply that with gravitational vector divided by Vg divided by S. So when I integrate the roll angle and multiply that G divided by Vg, I get the value of chi, which is cos. Now here, what I have is I have another summing junction, and this summing junction has a Kp and then this Kp has another summing junction, and here we add one integrator loop, which is Ki divided by S, and this integrator loop gets fed over here, and you have minus here, and then here you have this guy phi is coming from here. And then there is a control term, but that we will talk about in next class. But what I want you to do is, this is the partial. So there is one more transfer function before this. So at the end of the day, what I want to do is, this is what I want to do. I want to control the course angle of the aircraft. I want to decide what is the course angle of the aircraft. So at the end, I have the actual course angle, and here, before this transfer function, there is one more transfer function. Before this transfer function is the commanded course angle. And all these, whatever you have in between, they are the controller gains and the dynamics of the aircraft that is relating the actual commanded course angle with respect to the actual course angle. So now what I need to do is, the lateral control on the course means if I set up the course angle at 5 degrees, whatever may be the disturbances, whatever may be the dynamics, the aircraft should continue to go at 5 degrees of course angle. Now the next thing is, if the wind velocity changes, then as you can see, that value of Vg is going to change. That would change the actual course angle, but that will get fed back. There is another loop that will show you that will get fed back into the first original loop, and then the aircraft would correct itself. So in this particular lateral dynamics, what I'm trying to do is, I'm trying to control the course angle of the aircraft. If wind is completely zero, that means if the aircraft is flying indoors and there is no wind, then the course angle is equal to the yaw angle. So basically the course angle and yaw will be the same. But if there is wind present, aircraft is yawing in this direction, but aircraft would not follow that yaw direction. It will go a little bit offset. Okay. So again, there is a transfer function here, but what I want to show you here, this guy is called as the roll damping. Okay. So there are quite a few gains in this control logic. and let me list these gains. First gain is KD phi, which is the derivative gain on roll damping. Then we have the roll rate attitude is controlled with Kp phi and Ki phi. So basically you have a proportional gain and Ki phi. And finally, you have the coarse angle that is regulated with Kpx and Kix. So this is the gain on roll rate. This is the gain on roll, and these are the gains on the coarse. So coarse, roll, and this is roll damping gain. Now, how do you tune these gains? Typically, first we look at KD phi and KP phi. These are tuned first. Then Ki phi is gained, or its gain is tuned second. And finally, Kpx and Kix are gained last. And what I will do is, in the next class, we are going to look at each and individual transfer function, and then we will control it. And this exercise, even though may look tedious, it is very important, because there is a project wherein you have to actually, for your aircraft, you have to implement an autopilot. So basically, you would have a function called autopilot. That function would actually fly the aircraft in an autopilot mode. And if some of you want, then what you can do is you can actually convert that whole code into an MEX file, use MATLAB compiler, convert that into a hex file, and you are welcome to flash it onto a controller, or actually physical microcontroller. So, and you can actually fly. And there is a good exercise wherein you can do all that and flash the firmware of the Peacock autopilot using MATLAB. So I would like to show you the demo of that at some point. But what I'm going to do here is, the material I discussed today is a little intense. So I would encourage you to review this one more time. And in next class, what I'm going to do is, I'm going to use the technique that I showed over here to simplify and analyze each part of this long transfer function. Now, as promised in last class, if you have your simulation code working, I want to show you my code and answer any questions that you may have related to your current project. So let me see. So does anyone want to see any of my functions? Wind simulation? Yeah.
Previously you showed off the forces, and they had variable P in that.
Yeah.
And we'll have like U bar and whatnot.
Yeah.
You show where you get the P value.
Yeah. So this is the function. All these comments you want to ignore. So you have forces and moments where you have X, you have delta, you have wind value, and you have P. So X are the states, Delta are the inputs, E is the elevator, A is the aileron, R is the rudder, and T is the throttle. And then you have this wind north, wind east, and wind south. And then you have the gust, which is UWG, VWG, and WWG. Next, what we need to do is we have to use the rotation transformation. This is the same, the direction cosine matrix that is given in the textbook. And then what we need to do is we need to find out the wind vector in the body frame. So it is very simple. So UWG, VWG, WWG, and you have these components of wind. And then what you do is you find out the component of wind in the body frame. Then you want to find the component of the wind in the inertial frame. Basically take the transpose and then transfer it back. Next part is compute the velocity relative to the air mass, which is UR, VR, WR. And once you have UR, VR, WR, what you have is you have the airspeed, you have the alpha, which is angle of attack, you have the beta, and you have this Q bar, which is the dynamic pressure, which is rho, P dot rho. P dot rho is the density that is defined in the structure P for the UAV, which is nothing but the air density multiplied by VA square. And then you have cosine alpha, sine alpha, and just a non-dimensional P, non-dimensional Q, and non-dimensional R. Then here, the first force that you have to map in the body frame is the gravitational force, the weight of the aircraft. The weight of the aircraft, which is P dot mass. P is the structure. P dot mass indicates the mass of that miniature air vehicle, MAV, multiplied by P dot mass. P dot gravity is the value of the gravity defined in the structure. So P is a structure. P dot gravity gives you the gravity in P. And then you use sine theta, cosine theta, sine phi, cosine theta, cosine phi to find out the forces, effects. So three components of forces. So 1, 2, and 3. And then what you do is you basically find the lift and drag forces. So you can actually, we can use a simple linear model and then find out the lift and drag forces. And these are the exact same equation that are given in the textbook. AR is the aspect ratio, which again comes from P dot S underscore wing, P dot B square, which is width of the wing. And finally, you have this P dot C, dP. These are the coefficients that are defined for the coefficient of drag. And then you find out the lift force. Then you find the drag force. And then finally, what you do is you add that lift and drag force. Sorry, you add the lift and drag force, which is the aerodynamic force, to force 1. So at this point, force 1, you are updating the gravitational force with the aerodynamic force. Are you with me so far? If you go down, and these equations may look scary or intimidating, but please understand these are the exact same equations given in the textbook. I just coded those. You implement the exact same thing for torque, which is L, M, and N. So this is the equation for torque 1, torque 2, and you have torque 3. And at the end, you want to find out the propulsive force, and you can find it in multiple ways. So for that, this is the function. The name of the function is prop thrust torque. The input to that is VA, which is the airspeed, throttle, and P value. Why do we need to supply the P value? Because the propeller parameters are defined in that structure P. So we have to pass that structure. And at the end, the output of that function would be what is the thrust of the prop, what is the torque of the prop, what is the prop speed, and what is the motor current. And then what you do is you have forces, force 1 and torque 1, you get prop thrust and prop torque. Please understand, prop is fixed to the body frame. The torque given by prop will be about the x-axis of the aircraft. So the torque given by the prop would be about the x-axis of the aircraft, and force given by prop, or which is called as thrust, is going to be around in the x direction. That's why this force 1 term only gets modified. There is no force 2 or force 3. You don't have a prop that kind of tilts. Okay, so there is prop is going to give you thrust only in the direction of aircraft X. Okay, once everything else you can ignore, if at the end your output is going to be the force vector, the torque vector, then you are going to have the airspeed, angle of attack, side slip angle, Wn, We, and Wd. Everyone understood this function? Yeah. Oh, P structure comes from, I thought you used the exact same structure when you simulated your UAV, no?
It's not, it's the
MAV, yeah, that is MAV.
So to be able to.
It's in the, I think I uploaded the zip file corresponding to the template. So if you go to Canvas, there is a zip file with all these template codes.
And it's in it now, not.
Yeah, it's MAV for your case.
It gets passed as a function argument, and then in the function argument, it is. Oh, so I'm not having that issue. It's not.
Yeah. You can call it MAV. That won't change the implementation. That will be the same. Okay. Any other function you guys want to see? Yeah. I don't know if you have experienced. The code works every time, but when you want to demonstrate it, it doesn't work. So now what I'm gonna do is, clearly before coming to class, I run the code, but I'm gonna take a leap of faith. Oh, clearly. So yeah, as you can see that my MavSim chapter 4, the variable, it's not in the dependencies. So what I need to do is I need to go to RS2 desktop and make sure everything is in. And now I will try my luck. Okay. I wanted to fly this with a joystick. I already got the joystick, but I couldn't finish the code. Yes. Try with this. Minus 2.700 and then add delta t is equal to 1. It is full turn. And see how your aircraft is flying. See, now my aircraft started dipping down and doing crazy maneuver. Yeah.
So I thought the range of plot, they have these calculating and that.
Yes.
You need to input anything in there.
If you use that block, that wind code completely, you don't have to use at all. You can simplify this simulation very much if you use that block. Maybe that could be another good project. Like build this simulation from the aerospace block set. Oh, everyone knows, right? The top performing student from this class will automatically get an internship. So let me see. I would add that an optional project. And just so you know what internship in our lab means, it means job guarantee. Okay, I'm serious because everyone who comes knows that the students who are working with me are smarter than me, so they are going to hire them. Okay, too many jokes on the on the Zoom. So okay, does anyone want to see anything? Yeah. If you're sitting flying like this, your aircraft. Okay. Yeah, but if you want to compare apples to apples, oranges to oranges, you are welcome to stop by my office and you can compare my code with your code. And if you have got your code working, please help your classmates. It's not like it's not a competition. I want everyone to learn.
So I was looking at it because we talked yesterday,
Yes.
and they're all they're usually 0 2.